presentation video on EMC Guidelines. My name is Martin Lavachka, and in this video I'm going to talk about electrical distribution, earthing principles and structures, implementation, coupling mechanisms and countermeasures, and wiring recommendations. The system earthing arrangement must be properly selected to ensure the safety of life and property. The behavior of the different systems concerning EMC considerations must be taken into account. European standards recommend the TNS earthing system, which causes the fewest EMC problems for installations comprising information technology equipment. In the table, you can find the main characteristics of the different earthing systems. When an installation includes high power equipment, it is advised to install one or more transformers specifically for these systems. The electrical distribution must be organized in a star system, and all outgoing circuits must exit the main LV switchboard. Electronic systems must be supplied by a dedicated transformer in a TNS system. The diagram shows recommendations for separate distributions. Earthing principles and structures. This section deals with the earthing and equipotential bonding of information technology devices and other similar devices requiring interconnections for signaling purposes. Earthing networks are designed to fulfill several functions. They can be independent or operate together to provide one or more of the following: safety of persons concerning electrical hazards, protection of equipment concerning electrical hazards, a reference value for reliable, high-quality signals, and satisfactory EMC performance. The system earthing arrangement is generally designed and installed because of obtaining low impedance capable of diverting fault currents and high frequency currents away from electronic devices and systems. There are different types of system earthing arrangements, and some require that specific conditions be met. These conditions are not always met in typical installations. For professional and industrial installations, a common bonding network may be useful to ensure better EMC performance concerning the following points: digital systems and new technologies, compliance with the EMC essentials requirements of Directive 2004-108-EC, the wide number of electrical applications, and a high level of system safety and security, as well as reliability and availability for residential premises. It is now recognized that independent, dedicated earth electrodes, each serving a separate earthing network, is a solution that is not acceptable in terms of EMC, but also represents a serious safety hazard. In certain countries, the national building codes forbid such systems. The use of separate earthing network for electronics and earthing network for energy is not recommended because of obtaining the correct EMC, even when a single electrode is used. In the event of a lightning strike, a fault current or high frequency disturbances as well as transient currents will flow in the installation. Consequently, transient voltages will be created and result in failures or damage to the installation. If installation and maintenance are carried out properly, this approach may be dependable, but it is generally not suitable for EMC purposes and is not recommended for general use. The recommended configuration for the earthing network and electrodes is 2 or 3-dimensional. This approach is advised for general use both in terms of safety and EMC. This recommendation does not exclude other special configurations that, when correctly maintained, are also suitable. In a typical installation for a multi-level building, each level should have its earthing network and all the networks must be both interconnected and connected to the earth electrode. At least 2 connections are required to ensure that if one conductor breaks, no section of the earthing network is isolated. Practically speaking, more than 2 connections are made to obtain better symmetry in current flow, thus reducing differences in voltage and the overall impedance between the various levels in the building. The many parallel paths have different resonance frequencies. If one path has a high impedance, it is most probably shunted by another path with a different resonance frequency. On the whole, over a wide frequency spectrum, a large number of paths results in a low impedance system. Each room in the building should have earthing network conductors for the equipotential bonding of devices and systems, cableways, trunking systems, and structures. These systems can be reinforced by connecting metal pipes, gutters, supports, frames, etc. In certain special cases, such as control rooms or computers installed on false floors, ground reference planes or earthing strips in areas for electronic systems can be used to improve earthing of sensitive devices and protection interconnection cables. Implementation. Equipotential bonding inside and outside buildings. The fundamental goals of earthing and bonding are the following: safety, by limiting the touch voltage and the return path of fault currents, and EMC, by avoiding differences in potential and providing a screening effect. Stray currents are inevitably propagated in an earthing network. It is impossible to eliminate all the sources of disturbances for a site. Earth loops are also inevitable. When a magnetic field affects a site, differences in potential are created in the loops formed by the various conductors and the currents flowing in the earthing system. Consequently, the earthing network is directly affected by any countermeasures taken outside the building. As long as the currents flow in the earthing system and not in the electronic circuits, they do no damage. However, when earthing networks are not equipotential, the high-frequency stray currents will flow wherever they can, including in control wires. Equipment can be disturbed, damaged, or even destroyed. The only inexpensive means to divide the currents in an earthing system and maintain satisfactory equipotential characteristics is to interconnect the earthing networks. This contributes to better equipotential bonding within the earthing system, but does not remove the need for protective conductors. To meet legal requirements in terms of the safety of persons, sufficiently sized and identified protective conductors must remain in place between each piece of equipment and the earthing terminal. What is more, with the possible exception of a building with a steel structure, a large number of conductors for the lighting rods or the lighting protection network must be directly connected to the earth electrode. The fundamental difference between a protective conductor and a lighting rod down conductor is that the first conducts internal currents to the neutral of the MV-LV transformer, whereas the second carries external current to the earth electrode. In a building, it is advised to connect an earthing network to all accessible conducting structures, namely metal beams and door frames, pipes, etc. It is generally sufficient to connect metal trunking, cable trays, and lintels, pipes, ventilation ducts, etc. at as many points as possible. In many places where there is a large amount of equipment and the size of the mesh in the bonding network is greater than 4 meters, an equipotential conductor should be added. The size and type of conductor are not of critical importance. It is imperative to interconnect the earthing networks of buildings that have shared cable connections. Interconnection of the earthing networks must take place via several conductors and all the internal metal structures of the buildings or linking the buildings. In a given building, the various earthing networks must be interconnected to form a single equipotential bonding network. This earthing network must be as meshed as possible. If the earthing network is equipotential, the differences in potential between communicating devices will be low and a large number of EMC problems disappear. Differences in potential are also reduced in the event of insulation faults or lighting strikes. If equipotential conditions between buildings cannot be achieved, or if the distance between buildings is greater than 10 meters, it is highly recommended to use optical fiber for communication links and galvanic insulators for measurement and communication systems. These measures are mandatory if the electrical supply system uses the IT or TNC system. Improving equipotential conditions. Bonding networks. Even though the ideal bonding network would be made of sheet metal or fine mesh, experience has shown that for most disturbances, a 3-meter mesh size is sufficient to create a mesh bonding network. Examples of different bonding networks are shown in figure R7. The minimum recommended structure comprises a conductor surrounding the room. The length of connections between a structural element and the bonding network does not exceed 50 centimeters, and the additional connection should be installed in parallel at a certain distance from the first. The inductance of the connection between the earthing bar of the electrical enclosure for a set of equipment and the bonding network should be less than 1 microhenry. For example, it is possible to use a single 50 centimeter conductor or 2 parallel conductors 1 meter long installed at the minimum distance from one another to reduce the mutual inductance between the two conductors. Where possible, the connection to the bonding network should be at an intersection to divide the high frequency currents by 4 without lengthening the connection. The profile of the bonding conductors is not important, but a flat profile is preferable. The conductor should also be as short as possible. Parallel earthing conductor. The purpose of a parallel earthing conductor is to reduce the common mode current flowing in the conductors that also carry the differential mode signal. The parallel earthing conductor must be designed to handle high currents when it is used for protection against lighting or the return of high fault currents. When cable shielding is used as a parallel earthing conductor, it cannot handle such high currents, and the solution is to run the cable along metal structure elements or cableways, which then act as other parallel earthing conductors for the entire cable. Another possibility is to run the shield cable next to a large parallel earthing conductor with both the shield cable and the parallel earthing conductor connected at each end to the local earthing terminal of the equipment or the device. For very long distances, additional connections to the network are advised for the parallel earthing conductor at irregular distances between the devices. These additional connections form a shorter return path for the disturbing currents flowing through the parallel earthing conductor. For U-shaped trays, shielding and tubes, the additional connection should be external to maintain the separation from the interior. Bonding conductors. Bonding conductors may be metal strips, flat bands, or round conductors. For high-frequency systems, metal strips and flat braids are preferable because a round conductor has a higher impedance than a flat conductor with the same cross-section. Where possible, the length-to-width ratio should not exceed 5. The physical separation of high and low current cables is very important for EMC, particularly if low current cables are not shielded or the shielding is not connected to the exposed conductive parts. The sensitivity of electronic equipment is in large part determined by the accompanying cable system. If there is no separation, the electromagnetic coupling is at its maximum. Under these conditions, electronic equipment is sensitive to EMC disturbances flowing in the affected cables. Use of busbar trunking systems such as canales or busbar ducts for high power ratings is strongly advised. The levels of radiated magnetic fields using these types of trunking systems are 10 to 20 times lower than standard cables or conductors. Raised floors. The inclusion of the floors in the mesh contributes to the equipotentiality of the area and consequently to the distribution and dilution of disturbing low frequency currents. The screening effect of a raised floor is directly related to its equipotentiality. If the contact between the floor tiles is poor, or if the contact between the support brackets is faulty, it is necessary to add an equipotential mesh. In this case, it is sufficient to ensure effective electrical connections between the metal pedestals. Small spring clips are available on the market to connect the metal pedestals to the equipotential mesh. Ideally, each pedestal should be connected, but it is often sufficient to connect every other pedestal in each direction. A mesh of 1.5 to 2 meters in size is suitable in most cases. The recommended cross-sectional area of the copper is 10 mm squared or more. In general, a flat brace is used. To reduce the effects of corrosion, it is advised to use tin-plated copper. Perforated floor tiles act like normal floor tiles when they have a cellular steel structure. Preventive maintenance is required for the floor tiles approximately every 5 years. Rubber or polymer antistatic joints must be maintained, similar to the bearing surfaces of the floor tiles. Cable running. Selection of materials and their shape depends on the following criteria: severity of the EM environment along cableways, authorized level or conducted and radiated emissions, type of cables, EMI withstand capacity of the equipment connected to the wiring system, other environmental constraints, and future extensions planned for the wiring system. Non-metal cableways are suitable in a continuous low-level EM environment, a wiring system with a low emission level, situations where metal cableways should be avoided, and systems using optical fibers. For metal cableways, it is the shape rather than the cross-sectional area that determines the characteristic impedance. Closed shapes are better than open shapes because they reduce common mode coupling. Cableways often have slots for cable straps. The smaller the better. The types of slots causing the fewest problems are those cut parallel and at some distance from the cables. Slots cut perpendicular to the cables are not recommended. In certain cases, a poor cableway in EMI terms might be suitable if the EM environment is low, if shielded cables or optical fibers are employed, or if separate cableways are used for the different types of cables. It is a good idea to reserve space inside the cableway for a given quantity of additional cables. The height of the cables must be lower than the partitions of the cableway. Covers also improve the EMC performance of cableways. In U-shaped cableways, the magnetic field decreases in the two corners. That explains why deep cableways are preferable. Different types of cables should not be installed in the same bundle or in the same cableway. Cableways should never be filled to more than half capacity. It is recommended to electromagnetically separate groups from one another, either using shielding or by installing the cables in different cableways. The quality of the shielding determines the distance between groups. If there is no shielding, sufficient distances must be maintained. The distance between power and control cables must be at least 5 times the radius of the larger power cable. Metal building components can be used for EMC purposes. Steel beams often form uninterrupted earth structure with large transversal sections and surfaces with numerous intermediate earthing connections. Cables should, if possible, be run along such beams. Inside corners are better than the outside surfaces. Both ends of metal cableways must always be connected to the local earth network. For very long cableways, additional connections to the earthing systems are recommended between connected devices. Where possible, the distance between the earthing connections should be irregular to avoid resonance at identical frequencies. All connections to the earthing systems should be short. Metal and non-metal cableways are available. Metal solutions offer better EMC characteristics. A cableway must offer a continuous, conducting metal structure from beginning to end. An aluminium cableway has a lower DC resistance than a steel cableway of the same size, but the transfer impedance of steel drops at a lower frequency, particularly when the steel has a high relative permeability. Care must be taken when different types of metal are used, because the direct electrical connection is not authorized in certain cases to avoid corrosion. That could be a disadvantage in terms of EMC. When devices connected to the wiring system using unshielded cables are not affected by low frequency disturbances, the EMC of non-metal cableways can be improved by adding a parallel earthing conductor inside the cableway. Both ends must be connected to the local earthing system. Connections should be made to a metal part with low impedance. The pack should be designed to handle high faults and common mode currents. Implementation. When a metal cableway is made up of several short sections, care is required to ensure continuity by correctly bonding the different parts. The parts should be preferably be welded along all edges. Riveted, bolted, or screwed connections are authorized as long as the contact surfaces conduct current and are protected against corrosion. Tightening torques must be observed to ensure correct pressure for the electrical contact between two parts. When a particular shape of cableway is selected, it should be used for the entire length. All interconnections must have a low impedance. A single wire connection between two parts of the cableway produces a high local impedance that cancels its EMC performance. Starting at a few megahertz, a 10 cm connection between two parts of the cableway reduces the attenuation factor by more than a factor of 10. Each time modifications or extensions are made, it is very important to make sure they are carried out according to EMC rules. Covers for metal cableways must meet the same requirements as those applying to the cableways themselves. A cover should have a large number of contacts along the entire length. If that is not possible, it must be connected to the cableway at least at the two ends using short connections. When a cableways must be interrupted to pass through a wall, low impedance connections must be used between two parts. Busways. Busways reduce the risk of exposure to electromagnetic fields. According to the World Health Organization, exposure to electromagnetic fields can be a health hazard starting at the levels as low as 0.2 microteslas and could represent a long-term risk of cancer. Some countries have created standards that stipulate limits. All electrical conductors generate magnetic fields proportional to the distance between them. The design of busbar trunking with tightly spaced conductors in a metal enclosure helps to considerably reduce radiated electromagnetic fields. The electromagnetic field characteristics of busbar trunking are well defined and measurements show that they are far below potential dangerous levels. In specific cases where particularly low values are required, it is important to minimize the magnetic induction generated by power cables. Magnetic induction is proportional to the current, proportional to the distance between the conductors, and inversely proportional to the square of the distance to the bus bar. A bus bar with a steel casing provides a good screening effect compared to power cables. The magnetic field is reduced from 10 to 30 times depending on the catalyst model. This is particularly low because of the short distance between the bars and the additional attenuation provided by the steel casing. When the decision is made to use shielded cables, it is also necessary to determine how the shielding will be bonded, otherwise the benefits are considerably reduced. To be effective, the shielding should be bonded over 360 degrees. Figure R17 shows different ways of earthing the cable shielding. For computer equipment and digital links, the shielding should be connected at each end of the cable. The connection of the shielding is very important for EMC. If the shielded cable connects equipment located in the same equipotential bonding area, the shielding must be connected to the exposed conductive parts at both ends. If the connected equipment is not in the same equipotential bonding area, there are several possibilities. Connecting only one end to the exposed conductive parts is dangerous. If an insulation fault occurs, the voltage in the shielding can be fatal for an operator or destroy equipment. In addition, at high frequencies, the shielding is not effective. Or connection of both ends to the ECPs can be dangerous if an insulation fault occurs. A high current flows in the shielding and can be damaged. To limit this problem, a parallel earthing conductor must be run next to the shielded cable. The size of the parallel earthing conductor depends on the short circuit current in the given part of the installation. It is clear that if the installation has a well-meshed earthing network, this problem does not arise. The following figure R18 shows how to prepare the screen when the EMC clamps are used. Communication networks. It is highly recommended to follow the European standards EN 50173 series to perform information technology cablings. To ensure a reliable data transmission, the quality of the whole link should be homogeneous. That means the category of the different cables should be the same and the connecting interfaces should be adapted to the cables. Cables and connection of different categories may be mixed within a channel, however, the resultant performance will be determined by the category of the lowest performing component. The shielded continuity of the whole link should be ensured and controlled by tests. The terminal outlets could be used to earth the screen terminations in the cabinet. The choice of these terminal outlets is very important. Communication networks are mostly extensive. They interconnect equipment located in different areas where the feeding power supplies could have different earthing systems. This figure demonstrates how to reduce disturbing current loop. If these different areas are not well equipotential, harsh transient currents could appear, causing high voltage potential differences between interconnected equipment. Communication interfaces could be disturbed or damaged by these common mode overvoltages. The use of a TNS earthing system and well-equipped installation minimize this issue. In any case, the use of SPD installed in common mode or differential mode is recommended. If the different areas are not equipotential, if the power supplying earthing system is TNC or IT, or if there is a doubt at the previous 2 points, optical fiber links are highly recommended. To avoid electrical safety issues, the optical fiber link should not have any metallic parts. Protection against coil disturbances. AC and mostly DC coils are very disturbing sources. To minimize these high-frequency disturbances, the TVS could be implemented. To be efficient, the TVS shall be installed closely to the coil. Cabinet cabling. Each cabinet must be equipped with an earthing bar or a ground reference metal sheet. All shielded cables and external protection circuits must be connected to this point. Any of the cabinet metal sheets or the DIN rail can be used as the ground reference. Plastic cabinets are not recommended. In this case, the DIN rail must be used as ground reference. Each panel shall be fitted as a minimum with an earthing bar and a reference metallic plate or a grounding plate. All the metallic parts shall be interconnected together with adapted futures. The use of a specific washer is recommended. Some examples of preferred ones are shown in figure R23. All the cables shall be laid on the earth metallic structures. All EMC components shall be fixed directly on the metallic plates without any insulating coating. Screened cables coming or going out from the panel shall be bonded to the earthing bar or grounding plate if these cables are coming from long distances or non-equipotential zones. The goal is to divert the disturbing currents at the cabinet entrance and not inside the cabinet. Non-metallic cabinets are not recommended for EMC purposes. To protect electronics equipment against low-frequency magnetic fields, it is recommended to use galvanized steel cabinets. Non-magnetic metals are more efficient for high-frequency environments. Power and low-level apparatus should be physically separated, and cable segregation and distances between power and sensitive cables should also be respected as shown in the figures R26 and R27. It is absolutely essential to specify the standards and recommendations that must be taken into account for installations. Below are several documents that may be used. Electrostatic discharge protection. Normally, the use of specific tools or packages is required to handle or carry electronic boards or components that are sensitive to electrostatic discharge. Our products comply with standards ESD test, but ESD conditions are in some cases over the specs. ESD threat could cause semiconductor aging and failures. Without any care, the semiconductor devices could be damaged or burned without users noticing. The use of a specific anti-ESD wrist strap is highly recommended. This wrist strap should be installed inside each cabinet and correctly connected to the earthed cabinet metallic frame. Static electricity is produced by the contact and separation of materials, shoes and floors, clothes and the human body, and parts being moved on or from surfaces. The generated charge will reside on the body until it is discharged. The familiar zap that all of us have experienced is the zap that does the damage. If we can prevent any static charge from building up on the body, then there's essentially nothing to be discharged. A properly grounded wrist strap effectively prevents any static charge from building up. Any static charge that would tend to be created is instantly drained by the wrist strap. The wrist strap maintains the potential equilibrium that is accomplished the hard way with the zap. Coupling mechanisms and countermeasures. An EM interference phenomenon must be summed up in a figure R29. The different sources of disturbances are radio frequency emissions, electrical equipment, power systems, lighting, electrostatic discharges, electromagnetic nuclear pulses, for example. The potential victims are radio and television receivers, radar, wireless communication systems, analog systems, digital systems, the different types of coupling are common mode impedance coupling, capacitive coupling, inductive coupling, and radiated coupling. Common mode impedance coupling happens when two or more devices are interconnected by the power supply and communication cables. When external currents flow with these common mode impedances, An undesirable voltage appears between points A and B, which are supposed to be equipotential. This stray voltage can disturb low-level or fast electronic circuits. All cables, including the protective conductors, have an impedance, particularly at high frequencies. Common mode impedance coupling occurs when devices linked by a common reference conductor are affected by fast or intense current variations, or there is a common return path for several electrical sources. If they cannot be eliminated, common mode impedances must at least be as low as possible. To reduce the effects of common mode impedances, it is necessary to reduce impedances by meshing the common references, use short cables or flat braids which for equal sizes have a lower impedance than round cables, or by installing functional equipotential bonding between devices, or reduce the level of the disturbing currents by adding common mode filtering and differential mode inductors. Capacitive coupling. The level of disturbance depends on the voltage variations and the value of the coupling capacitance between the disturber and the victim. Capacitive coupling increases with the frequency, the proximity of the disturber to the victim and the length of the parallel cables, the height of the cables for a ground referencing plane, the input impedance of the victim circuit, and the insulation of the victim cable, particularly for tightly coupled pairs. Figure R33 shows the results of capacitive coupling between two cables. Capacitive coupling occurs nearby cables subjected for rapid voltage variations, startup of fluorescent lamps, high voltage switch mode power supplies, or coupling capacitance between the primary and secondary windings of transformers, crosstalk between cables. Countermeasures are limit the length of parallel run of disturbers and victims to a strict minimum, increase the distance between the disturber and the victim. For two-wire connections, run the two wires as close together as possible. Position a peg bonded at the both ends and between the disturber and the victim. Use 2 or 4 wire cables rather than individual conductors. Use symmetrical transmission systems on correctly implemented symmetrical wiring systems. Shield the disturbing cables, the victim cables, or both. Or reduce the dV-dt of the disturber by increasing the signal rise time where possible. Inductive coupling is when the disturber and the victim are coupled by a magnetic field. The level of disturbance depends on the current variations and the mutual coupling inductance. Inductive coupling increases with the frequency, the proximity of the disturber to the victim and the length of the parallel cables, the height of the cables for a ground referencing plane, and the load impedance of the disturbing circuit. Inductive coupling occurs when nearby cables are subjected to rapid current variations, short circuits, fault currents, lighting strikes, stator control systems, welding machines, or inductors. Countermeasures are: limit the length of parallel runs of disturbers and victims to a strict minimum, increase the distance between the disturber and the victim. For two-wire connections, run the two wires as close together as possible. Use multi-core or touching single-core cables, preferably in a triangular layout. Position a PEC bonded at both ends and between the disturber and the victim. Use symmetrical transmission systems on correctly implemented symmetrical wiring systems. Shield the disturbing cables, the victim cables, or both. Reduce the dV/dt, the disturber, by increasing the signal rise time where possible. Or PTC resistors on the disturbing cable, ferrite rings on the disturbing or victim cable. Radiated coupling is when the disturber and the victim are coupled by a medium. The level of disturbance depends on the power of the radiating source and the effectiveness of the emitting and receiving antenna. An electronic field comprises both an electrical field and a magnetic field. The two fields are correlated. It is possible to analyze separately the electrical and magnetic components. The electrical field and the magnetic field are coupled in wiring systems via the wires and loops. When a cable is subjected to a variable electrical field, a current is generated in the cable. This phenomenon is called field-to-cable coupling. Similarly, when a variable magnetic field flows through a loop, it creates a counter electromotive force that produces a voltage between the two ends of the loop. This phenomenon is called field-to-loop coupling. Radiated coupling occurs with radio transmission equipment, radar, automobile ignition systems, arc welding machines, induction furnaces, power switching systems, electrostatic discharges, or lighting. To minimize the effect of radiated coupling, the measures for field-to-cable coupling are: reduce the antenna effect of the victim by reducing the height of the cable concerning the ground referencing plane. Place the cable in an uninterrupted bonded metal cableway. Use shielded cables that are correctly installed and bond. Add PECs and place filters or ferrite rings on the victim cable. The measure for field-to-loop coupling is: reduce the surface of the victim loop by reducing the height and the length of the cable. Use the solution for field-to-cable coupling. Use the Faraday cage principle. Radiated coupling can be eliminated using the Faraday cage principle. A possible solution is shielded cable with both ends of the shielding connected to the metal case of the device. The exposed conductive parts must be bonded to enhance effectiveness at high frequencies. Radiated coupling decreases with the distance and when symmetrical transmission links are used. Wiring recommendations. Internal signals can be grouped into four classes. Class 1 includes main power lines, power circuits with a high dIdt, switch mode converters, or power regulation control devices. This class is not very sensitive but disturbs the other classes. Class 2, which includes relay contacts. This class is not very sensitive but disturbs the other classes. Class 3, which includes digital circuits. This class is sensitive to pulses but also disturbs the following class. Class 4 includes analog input-output circuits. This class is sensitive. It is a good idea to use conductors with a specific color for each class to facilitate the identification and separate the classes. This is useful during design and troubleshooting. Cables carrying different types of signals must be physically separate. Disturbing cables must be placed at some distance from the sensitive cables. A cable should carry the signals of a single class. It is advised to overshield disturbing and sensitive cables. Avoid using a single connector for different classes. All three conductors must always be bonded at each end. The two conductors must be installed as close together as possible. Cables must always be positioned along their entire length against the bonded metal parts of devices. The use of correctly bonded metal trunking considerably improves internal EMC. We come to the end of this presentation. Thanks for watching.